So today we're going to introduce you to the piece of hardware that you're going to use sort of as the base of your payload, which is the MegaSat development board that was developed here at LSU. So it's just a microprocessor development board that's designed to basically give students a base to build a payload upon, build upon the electronic instrumentation you were introduced to last semester and programming that you were introduced to last semester, and then be able to, expand upon that. That board was developed here at LSU by LaSpace staff, and it's a replacement for an older board called the MegaSat, which had a similar function but was just based on some older hardware that was starting to show its age. So sort of the history of this program and development boards goes back to something that was called the CanSat. It was a project developed by a professor at Stanford named Bob Twiggs in the late 90s. And the reason it was called a CanSat is because it would basically fit inside of a soda can. It was a little satellite you could build inside of a soda can. In the early 2000s, some electronics shop staff here at LSU, Brad Ellison and Jim Giamanco, took that CanSat and sort of expanded upon it and created the MegaSat. So for this program, we needed different capabilities that was from the CanSat. So that's why the MegaSat was developed. And that was used for many years, I think 15 roughly at this point. But it was based on some pretty old hardware, and it's starting to show its age. And then there's some, more modern techniques that students could learn. So that's why the MegaSat was created. So this is a picture of the original CanSat. So your actual microprocessor is this thing right here. It's called a basic stamp. And then you had, a few other integrated circuits for memory and doing things like analog to digital conversion and a real-time clock. And in particular, it was also made to connect to a radio modem. But in general, ACE's payloads aren't transmitting over radio. We try to keep that for the beacons, and usually the way student payloads work is you record your data on board your payload. So because we didn't need the modem and there was some other stuff that we would have liked to have students have the capability, that's why the CanSat was developed into the MegaSat. So this is what the MegaSat board looked like. If there were previous LACES programs at your schools, you may even have some version of this old version of this board lying around. So what it had a basic stamp for the microcontroller. That's what would sit in this socket right here. It would have a external EEPROM. That would be your, permanent storage where you could write data to. It had a 4-channel analog to digital converter, a voltage reference, a temperature sensor, a real-time clock with a battery backup. That's what the battery right here is for. And a few LEDs. Additionally, you had this little prototyping area so students could, basically add capabilities to their payload and develop it. And like I said, we use this particular hardware for over 10 years. before it was decided to it was time to update to a more modern microcontroller. So this is what your MegaSat should hopefully look like eventually when you get done. So this is designed to stack on top. So it's a shield, so it'll stack on top of the Mega. That's why it's called a MegaSat. So on the bottom here is an Arduino Mega, which is below the MegaSat board. And then on top of it, you can see you have your GPS shield. And then this is the jumper, if you recall, that we used last time, last semester, to be able to connect to another serial port on the Arduino. So you have this standard footprint of Arduino pins, where you can solder in your header pins and be able to stack any standardized shield and also stack it into your Arduino. So that's your Arduino Mega interface. You have a real-time clock, which is right here, which gives you the ability to keep your time if you even when your payload is powered on and off. It has built-in a number of built-in sensors. So there's two temperature sensors, sort of designated as internal and external, but by no means are you required to use them that way. You can use them how you wish. There is this amplifying circuit for connecting a 3-pin humidity sensor. And then finally, there is a circuit here which you will use the pressure detector, the same ones that you used at the end of last semester. And all of the amplifying circuitry is built in, and it's routed to each of the outputs of those circuits is routed to one of the analog pins on the Arduino. So this is, just a circuit schematic of the pins of your real-time clock. The particular model number is that Maxim DS3231. You read this real-time clock and send commands to it over the I2C. So you're going to be needing to use those I2C libraries that you learned about last semester. And basically what the real-time clock gives you is it gives you a very accurate time. So it's not going to drift. So one of the things that it uses is it'll compensate its oscillator for temperature changes, so you don't basically have your clock speed up or slow down as it cools. And so it's got the way that you use these things, and you'll see this when you actually get to the real-time clock activity. You basically set a date and time as now, and then it'll keep time from that, just like a clock. You set it, and then you can read out what the current time is based on that. So you've got the specs basically that this thing should operate fine over the entire payload flight. -40 to 85C. If you look at some graphs of the tropopause temperature, that might get down to -52, but that's the air temperature outside of the payload, and that's a relatively small region that you're passing through rapidly. So anything internal to your payload should not be getting below -40. The next sort of major component, you have a combination accelerometer and gyroscope. So the accelerometer basically tells you in 3 axes, X, Y, Z, what is the acceleration being felt. That will also include the gravity. So normally, if you're not doing anything strange, you should be able to see 1G straight down. The gyroscope gives you basically rotation around 3 axes. So it'll measure out in degrees how quickly you're rotating. And again, this is also interfaced through the I2C. And in fact, by default, it comes with the same address as the real-time clock. So one of the steps of your assembly is going to basically be to desolder and resolder a jumper on that accelerometer board, which will change the address such that the real-time clock and the accelerometer have a different address. But similarly, you'll send commands and you'll read this thing out over an I2C interface. There's, several different scales you can set these on, basically 4 different scales from lowest to highest. So this is 200, 500, 1,000, and 2,000 degrees per second, right? So based on what you're expecting, you'll send a command to this thing and tell it, I want the output on one of these scales. Similarly, you get 4 different scales for your accelerometer, where basically the max values are plus or minus 2G, 4G, 8G, or 16G. So one thing is both of those components actually run on 3.3 volt, which means their I2C pins are on 3.3 volt. However, if you recall, the Arduino I2C, all of its logic pins run on 5-volt logic. So one of the chips ICs that you'll be soldering on is a level shifter. So on this side of the level shifter, it'll be 5-volt logic, and on this side, it'll be 3.3-volt logic. It'll have the same pulse shape on both sides, but it just shifts the value for the high or low. The particular model used is a Texas Instrument TCA 9517. And importantly, this is a bi-directional level shifter. Sometimes you'll get level shifters that are only one way. And it also has a bit of a buffer built into this, right? So it basically reads the signal coming in and stores it for a little bit and then transmits it back out. And it'll work basically up to the maximum speed of fast mode I2C, which is 400 kilohertz. If you recall, the I2C had a clock speed that you can set, and fast mode is the defined standard at 400 kilohertz. There's also other speeds, so standard mode, I don't remember what the clock speed is for that because you pretty much always use the 400 kilohertz. Like I said, you have 2 temperature sensors. These are very similar to the temperature sensors you used for the capstone project at the end of the semester. The actual temperature sensor is just a silicon PN junction diode. And then you have a amplifying circuit that should look very similar to the one that you used for your capstone project. It's slightly different, but it'll have one resistor that'll adjust its gain. Notably, this circuit will also uses a current source. So we sort of were sloppy when we did the capstone because we weren't trying to make a real precision instrument, but for this diode voltage drop to only be a function of temperature, we really want to have a constant current going through it. And that is why you have this current source here. But other than that, you have basically the same output with a non-inverting amplifier with an offset, so you can fully set this 0.15 voltage to a full 5-volt range. And this is going to go to one of your analog pins. In particular, the one that's drawn here goes to the Arduino pin A1. That's what this MA1 means. You also have a Honeywell humidity sensor. So if you look at that, you'll see that you get a linear output voltage that varies with relative humidity. You have a similar amplifying circuit, and again, that's going to go through the MegaSat board directly into one of the analog pins of the Arduino through the header pins that you have to solder in. Your pressure sensor, like I said, is the same pressure sensor that you used in the capstone project. So that's your pressure sensor right here. And you can see again on this one, we're actually using a current source for the same sort of reasons that you do for the diode, so that the only actual changes in voltage of the output are due to the changes in pressure and not the slight changes in current that happen when you change the resistances there. So, but it's the exact same thing. You'll see that you have these two single stage amplifiers and then a second stage differential amplifier. This one is slightly different in that the way that you adjust the gain of the signal is you'll actually adjust the gain of one of the amplifiers rather than adjusting the gain on this differential. And that is it for your introduction to the Arduino or the LSU MegaSat.